Alright, so in this video we're going to go over how to clear out a linked list. Here's the struct, and here is the implementation that we're using for the linked list. So I'm first going to start with a recursive implementation of clearing a linked list. I just want to remind you that, well, first of all, this is not using a class, but just writing a code that can clear any linked list that's built in main. So here I'm calling the build and the print functions that we already wrote in previous videos. So we have a linked list that's built, and then we've also printed it to make sure that it looks good. And now we're going to delete. Now the idea here is that we're just going to write a function that deletes anything that's passed in. So it's going to walk through an entire list until it gets to a null pointer, and it's going to remove the memory for each of those. So the recursive implementation is interesting. Again, you don't want to use it on really long lists because it won't work, but it's always good practice to practice everything recursively. So if we pass in a pointer to the front of this list into this function here, which is what's getting called in main. Our base case is once we hit the null pointer, we know we've reached the end of the list. And this is actually going to kind of back out of it, and that's how it's going to get through and delete it. You have to be careful when you work with linked lists that you don't delete something before you need it. So the idea of this recursive call is that it's actually going to recurse all the way through to a null. So it's going to call the list next and send it into the recursive call and go through again. Then it's going to do it again to the third one, and then it's going to do it again until it gets to the null pointer. So here we've reached the base case, and once you reach the base case it actually backs out, and then you're under the recursive call, and then it goes back and it deletes each of the elements. By going backwards through recursing backwards through a list in order to delete it is the only way to do it. If you deleted before you recursed through, you would have lost the link to that list. So recursion is really nice for this reason. Like, this is such clean code. You know, it's just like it's very satisfying. But if we were to reverse these lines, what would happen is that we would delete the list before we move to its next, the list being the pointer to the node, and then we wouldn't be able to find it anymore. So if we you know, did this in the reverse order, basically it would first delete list, which is the first one, and now you no longer have this. This is gone, you just deleted it. So there's no way to then get to the next one to delete. And you have to be really, really careful about this with linked lists. Each node is your only way to the next node, right? So you have to do everything in the proper order in order to get to that node or to delete it. But this does properly destruct a linked list. If you've ever written code in main of, you know, using a linked list, you probably, if you allocated on the heap, you probably didn't destruct your list. But now that we're writing classes with linked lists, you actually have to make sure that you destruct the list in your destructor. So this is kind of the idea of that. So let's look at the iterative clear of the linked list. So exact same thing, but instead of doing it recursively, we're just going to do it iteratively. Kind of fun to see it both ways. You can call it exactly the same way: build, print, and then delete. I mean, you don't have to print, but I'm just showing you all the things we've written so far. So here we're passing in list, which is the front of the list. Now this is where the order you have to be really careful about. So the first thing that you're going to do before you delete anything is you're going to create a next pointer that points to the next one in the list. You have to do that before you delete. Otherwise, if you delete, you can't access the next one. Once you delete, then you'll update the list pointer to next. So now we have list and next pointing to the same thing. Then you just do it again until you hit the null pointer. So first you save whatever the list points to next, then you delete what list points to, then you update what list points to. And then finally, on the last iteration, you save what the list's next points to, which in this case is a null. You delete what list points to, and then you update what list points to. Now list points to null, and so you're done. So you cannot swap these. They have to be in this order because it's the only way that you can destruct it. And again, you're going to want to iteratively destruct your lists because when you test on large inputs, you'll have Stack Overflow if you use the recursive implementation. Here's what it looks like in a class. So you'll notice that it's really, really similar, but there's a couple important differences. So I wanted to remind you of what the private member variables look like in the class. This is how you call it. Since this is an actual destructor, you won't see the destructor call, but when it goes out of scope, this is automatically going to be called. So the destructor works in a really similar way. First, we don't pass anything into the destructor. Instead, we already know where the front of the list is. It's a private member variable. And so we're just going to set a node pointer to the front. And you're going to want to do this because if you just move the front pointer, then you'll have lost it. And in some cases in the destructor that might be okay, but it's always good practice to just make a copy of the front pointer and then move that copy. A pointer does not take up very much space, so making extra pointers is not an issue. We're also going to have a next pointer that's declared outside of the loop. And then we are going to basically have the exact same code that we had before, which just is going to, loop through each one and delete it. So the big difference is that you don't pass anything into the constructor, you just point to the front of the private member variable. A couple other things that are important with classes is that you do want to reset your other variables. It's good to reset front. You just destructed where front pointed to, right? When you destructed this node on that first call. So front now points to something that is no longer available. So it's a good style to always reset that to a null pointer, and then also set any other private member variables accordingly. So the size equals 0. If you're just writing a destructor, this is sort of unnecessary because it means that the object is out of scope and you're not going to use it anymore, and so front is not accessible and neither is size. However, clearing a linked list is something you might want to do outside of a destructor. So one tip I have is to write a public member function called clear that does this, and then your destructor can just call clear. This is handy for testing because you can test clear and make sure it's working as expected, but it also allows you to clear out an object and reset it in any way that you'd like. So that is the destructor. I'm not going to test this one in Memer, or maybe I should just run Valgrind really quick. Yeah, I'll do that. Hopefully it's still open. So we wrote this little bit of code here, so we can test the destructor by just running Valgrind, and I'd already built this, so I'm going to run Valgrind, and this is just running Valgrind on the parameterized constructor in print. So you'd want to keep doing this as you started implementing more functions. Oh no, this is the one where it just asked me how many. So here it's saying there were 8 Alex and 8 Freeze, so we are in good shape. I'm not really sure why there were 8 Alex though. Why were there 8? Only had 5, right? my main must call something else as well. But they're all destructed properly, so that's good. Okay, so that is it for clearing a linked list and writing a destructor.